Hello, Maurieo! In this video I'm going to be looking at calculating out a vertical curve. Vertical curves, they occur at the intersection of gradients in roads so that we have a nice transition from one gradient to another along the centre line of a road. So here we have one gradient coming up here at 5.2, and then it changes down to a gradient here of negative 3.2, and these curves give a nice transition from one gradient to the next without too much disturbance to the motorist, unlike the speed bump, which is definitely not a very good vertical curve. So we're going to calculate the even 20 metre reduced levels for this equal tangent vertical curve. The entry grade is plus 5.2% and the exit grade minus 3.2%. The curve is 170 metres long and the vertical intersection point has a chainage of 3 plus 50, which this is a way of recording chainages, where the 3 represents the 100 and the 50 obviously, so it's the equivalent of 350 metres, and an RL of 549 metres. So we have to calculate the RLs for the 20 metre even chainage stations plus the start and end of the vertical curve. Calculate the RL of the highest point on the curve. TP1 and TP2 are tangent points. So first thing is to find out, or calculate out the chainage of the start of the curve. So that is 3 plus 50, which is the vertical intersection point, minus 170 by 2, the length of the curve, which is 85. So that is a chainage of 2 plus 65. Similarly, the end of the curve is 3.5 plus 170, which is 4 plus 35, or 435. Most of us are used, but this particular technique here is we need to examine that in this particular question. Now, to calculate the RL of TP1, of course, we just work backwards from the vertical intersection point. The gradient would be from there would be a negative 5.2%, so that's 549 minus 85 times 0.052, or 5.2%, so you could put in there 5.2 divided by 100, and I'd hope that you would get 0.052. And just working that out, we get 544.58. Similarly, working out the RL of TP2, it's 549 minus 85 times 0.032 for the 3.2% gradient. Now, A, which is the algebraic sum of the grades, is grade 1 minus grade 2, and this is done algebraically. So we've got grade 1 is 5.2%, minus negative 3.2%, so that adding as algebraically we get plus 8.4%. Now we need to calculate the RL of each station. Now the RL is equal to the RL plus the increase in height, delta H. So that's equal to the RL of TP1 plus, and we have a formula for delta H, which is my over 100 minus a y squared over 200L, where m is the gradient, or the initial gradient of the 5.2 there, the entry grade, and y is the length along the curve from TP1, and L is the length of the curve, in this case 170 meters, and m the entry grade plus 5.2%, and the length of the curve y from there will vary depending on which RL we want to calculate. So we now move along here to the final sheet in this one here, and so the first RL that we want to work out would be the even one, which would be the RL at 2 plus 80, which is 15 meters from TP1. So as I've worked out there, 2 plus 80 minus 15 meters. So we just use the formula 544.58 plus 5.2 times 15 over 100. So we've written the formula up here just so that it's on this sheet here. So 5.2 my over 100 minus 8.4 the grades there minus that would be remember that would be negative if it was a negative. In this case it is a positive quantity, and 15 squared over 200 L, we're 170. So we work all that out and we get 545.304. Now then it's just a matter of working out for every 20 meters thereafter, pretty much using the same formula. So rather than go through and do each one of those and show you how to do them, I just set up and did my answers in a spreadsheet here, which was pretty easy to work out actually. So I just set up a spreadsheet and went through every 20 meters till I came to, obviously earlier on I'd worked out that the end of the curve was 4 plus 3.5, so then we needed to just work out what the last one was, and then a further 15 meters on to 4 plus 3.5 there, which was 170, and there we get in a good agreement there with what our level was. So yeah, so there's our values all worked out just in a nice little neat spreadsheet, which probably not a bad way of doing it, although does not preclude you from working out individual solutions to each one with your calculator. Now we're also required to work out the highest RL, and there's a formula for that, and it's the RL TP1 plus length times m squared over 200a, just all the same values that we're used to. So we just go through and work that out, and it's 547.316. Now that's our highest value. So we could look at our table here, and we could see that it's possible that there could be a higher value in here between these, between in here, or 547.316. Just exactly where could that occur? It could occur in between here. It could also occur in between here if these ones are heading downwards. So the distance from TP1 to the highest RL is given by the formula LM over A, which comes out to be 105.238. So the station is 2 plus 65 plus 105.238, which is 3 plus 70.238, which would be in here. So it's between, the high point is between these two values here, and then it starts to duck off down here as well and get away. So there's where our highest value is. So there we are. We've calculated all of the RLs necessary for a vertical curve, a curve that makes has a lot of maths and science behind it, but essentially makes the ride for the road user, when we transition from one grade to the other, a gentle affair with good sight distances, where we don't lose sight of oncoming vehicles and that sort of thing. So